This is the lecture on section 11.4 on the comparison tests for infinite series. So the comparison tests, we're going to see two of those. There's the comparison test and then the limit comparison test. And what these are is that these are similar to the comparison tests that we saw for improper integrals, but we're going to use them for infinite series instead. And we'll do this first with the comparison test. So the comparison test. And I'm going to state this slightly differently from the way the book does it. And so what we're going to do is we're going to focus on a series with terms of the form an, and we're going to figure out strategies for deciding whether or not that series converges or diverges. So first, if 0 less than or equal to an less than or equal to bn, and the summation n equals 1 to infinity of bn converges, then the summation n equals 1 to infinity of an also converges. And again, similar to the comparison test for improper integrals, the point is that if this series converges, that's saying that I have something that's less than infinity here. And so if when I add up all of these terms I get something less than infinity, then when I add up all of these terms, I should also get something that's less than infinity. And on the other hand, if instead I have 0 less than or equal to cn less than or equal to the an that I care about, and I know that the series whose terms are the cn's diverges, then the series that I started with also diverges. So one thing to note here is that, like with the integral test, this comparison test only applies for series where the terms are all positive. Okay. So in section 11.5, we'll look at techniques for understanding what happens when a series has possibly negative or alternating terms. So let's look at an example of this. Let's decide whether or not the summation n equals 1 to infinity of 6 to the n over 5 to the n minus 1, does this converge or diverge? And the big idea with the comparison test is that you're going to start with a series that you have to decide about the convergence or divergence of, and you have to compare it to something. So you need to find another series to compare it to. And so when you're trying to figure out who to compare your series to, you need to ask yourself, what does this series remind me of? What does this series look like it wants to be? And the series to keep in mind right now, we really only have two types of series to think about. We have the geometric series and we have the p-series. And to me, if you look at this one, it looks like it really wants to be 6 to the n over 5 to the n. And that minus 1 as n gets larger and larger is contributing less and less to the terms of the series. So I'm going to compare this to the summation n equals 1 to infinity of 6 to the n over 5 to the n. And if we rewrite this, this is the summation n equals 1 to infinity of 6 over 5 to the n. And this is a geometric series with r equals 6/5, which is strictly greater than 1, so we know that it diverges. Now, in order to apply the comparison test, we need to show the following. We need to show that 6 to the n over 5 to the n is less than or equal to 6 to the n over 5 to the n minus 1. Right, so this is using part 2 of the comparison test, where I'm going to be comparing to a series that diverges. So I want to conclude that my original series diverges, and so I need to show that the one that I understand is less than or equal to the one that I want to understand. And once you boil it down to this situation, let me switch to the next page. We know that 6 to the n over 5 to the n is actually strictly less than 6 to the n over 5 to the n minus 1, because when you decrease the denominator by subtracting 1, you end up with a larger quotient. So in summary, the fact that summation n equals 1 to infinity 6 to the n over 5 to the n diverges, so the comparison test tells us that the summation n equals 1 to infinity of 6 to the n over 5 to the n minus 1 also diverges. Now, let's look at a similar example that asks about the summation n equals 1 to infinity of 6 to the n over 5 to the n plus 1. Now, this one is incredibly similar to the previous one, right? We would like to compare this to the same series, which diverges. So in order to apply the comparison test, we would need to show that 6 to the n over 5 to the n is less than or equal to 6 to the n over 5 to the n plus 1. And that's just not true. When you increase the denominator, you decrease the quotient. You don't increase it. This is not so. So the comparison test does not apply here. And this is where the limit comparison test comes in to help things out. So I'll explain that on the next page. So the limit comparison test is again a test for series with positive terms. And what we have to do is we have to take a limit. So we're going to say that L is the limit as n goes to infinity of an over bn. And we're going to assume that that limit is positive, and of course that it is a finite number. And the fact that that limit exists and that it's positive, not zero, and that it's finite, not infinite, is really crucial for this test to work in general. So those are the assumptions. And then the way the test gets applied is in two possible ways. First is that if the summation n equals 1 to infinity of bn converges, then the summation n equals 1 to infinity of an also converges. And similarly too, if the summation n equals 1 to infinity of bn diverges, then the summation n equals 1 to infinity of an also diverges. Okay. So notice that we don't have to check any inequalities here except for to make sure that the terms of the series are positive. The key to making this work is this limit of the ratio of the terms to be positive and finite. So for instance, let's look at our example, and I'm going to start this one on a new page to give us plenty of room to work. So I want to look at the sum n equals 1 to infinity of 6 to the n over 5 to the n plus 1. And I want to apply the limit comparison test with the series n equals 1 to infinity of 6 to the n over 5 to the n, which we know diverges. Okay. So in order to conclude that the series that we started with diverges, we need to compute the limit as n goes to infinity of the ratio of the terms from our series and let's actually do it the other way. Let's just do the terms from the series we care about divided by 6 to the n over 5 to the n plus 1, the series that we are interested in. So when we simplify this, the 6 to the n's cancel, and I put everything under a single denominator, we end up with limit as n goes to infinity of 5 to the n plus 1 over 5 to the n. And you can evaluate this limit in one of a couple of ways. One way would be to use L'Hopital's rule. Another way, though, is to just use a little bit of algebra. Right, so I can write this as 5 to the n over 5 to the n plus 1 over 5 to the n. And so that's the same thing as 1 plus 1 over 5 to the n. And as n goes to infinity, this bit goes to 0, so our limit ends up being just 1, which is certainly positive and finite. So we get to conclude from the limit comparison test that the series that we started with diverges. Okay. So notice that this technique is very similar to the technique with the comparison test, because first you look at your series and you say, what does that look like if I can't simplify it on my own? And then I'm going to compare it to a one that's a little bit friendlier. Let's see another example of this. So I want to consider the series given by summation n equals 2 to infinity 1 over n times the square root of n squared minus 1. Now, again, so that's n times n square root of n squared minus 1 in the denominator. And so the idea is to compare it, or limit compare, to something that is similar to it. And if you look at this series, as n gets larger and larger and larger, that minus 1 piece becomes negligible. And so this one is very similar to the summation whose terms are n times the square root of n squared, which simplifies to summation n equals 2 to infinity of 1 over n times n summation n equals to infinity of 1 over n squared. And this is a p-series with p equals 2, so we know that it converges. And so we guess, our suspicion is that the series that we started with converges as well. And so what I want to do is I want to see how would we apply the comparison test first in order to try and draw that conclusion. So what we need to show is that the series that we're comparing with, those terms are less than or equal to, we're trying to show that this converges, so we need to show that the terms that we care about are less than or equal to the ones that we are comparing to. Right? And again, the way to keep this in mind is the fact that this one converges is telling me that this series is less than infinity. So if I want to conclude that this one is also less than infinity, I need to do this inequality here. Okay, so this is true if and only if n squared is less than or equal to n times square root of n squared minus 1. And that's true if and only if n is less than or equal to square root of n squared minus 1. That's by canceling the positive factor of n. And since all these bits are positive numbers, I can square both sides, and that's if and only if n squared is less than or equal to n squared minus 1. Problem is that, like in the previous example, this here is false. Right? Number squared minus 1 is less than number squared, not greater than or equal to. And so the point is that the comparison test does not apply. We don't get to draw any conclusion from the comparison test. So we need to try the limit comparison test. And again, we're going to use the same series, so we're going to compare this one with this one, but we're going to use it, we're going to do the comparison with the limit style instead of the inequality style, which we'll do on the next page. So we were going to look at the summation n equals 1 to infinity of 1 over n times square root of n squared minus 1. We're going to compare that to the summation n equals 1 to infinity of 1 over n squared. And so to do that, we have to compute the limit as n goes to infinity of 1 over n squared, the thing we're comparing to, divided by the thing that we started with. Now, turning all of this into a single fraction, this is the limit as n goes to infinity of n square root of n squared minus 1 divided by n squared. I'll cancel one factor of n. Right, so cancel that n with the exponent 2 here. And if I bring that n inside the square root, I end up with the limit as n goes to infinity of the square root of 1 minus the quantity 1 over n squared. And as n goes to infinity, this bit goes to 0, and so we end up with this limit equals 1. I realize that n squared there got torgled. So that limit is positive and finite. So we get to conclude by the limit comparison test that the original series we started with also converges. And in the book you can see more examples of this in examples 1 through 4. So this is the end of the lecture on section 11.4 about the comparison tests.